This is Mike Vella welcoming you back to our practical problem-solving clinic on experimentation techniques. This is part 4 of the 5-part series. And in part 4, we'll provide a bit more of an introduction to Taguchi DOEs and then provide an example of a 6-factor DOE with one interaction considered. In section 3.5, we'll have a further introduction to the Taguchi designed experiment method. We'll have an example of an L8. We'll discuss the basic design and then go through a step-by-step example. Taguchi experiments come in several 2- and 3-level designs, a few 4- and 5-level designs, and even some mixed design, but the most popular used orthogonal arrays are the L4, L8, and the L16 2-level designs. Again, we would urge you to concentrate your use of L4 and L8s because they're much simpler to design and analyze. Although these orthogonal arrays differ in size and in some cases the number of factors, the good news is they share many common features. And given the limited time of this training series, we'll only go through the methods for an L8. Again, an emphasis on teamwork. Don't skimp on it. Planning the details of the experiment is absolutely the most critical part of any designed experiment. It's the advanced consideration of the experiment's design that will ultimately determine its effectiveness. It's common for users to become fixated or concerned about performing the calculations to the exclusion of planning. Let's worry about the calculations later. Consider the construction of the design first. The good news is use of higher math is not necessary for designed experiments. We're not going to be using calculus or anything like that. All that's required is addition, subtraction, and so forth. ANOVA, or analysis of variance, is broken down into steps and can be understood without the assistance of an expert. And for the analysis part and the calculations part, reliable software is available. You simply sign up for it and pay a little money, and the package will be in your inbox. Here's an example. Consider the photograph on the right is a typical fiberglass shower enclosure. You are part of a research and development team working to increase the bonding strength of sprayed applied fiberglass. Bonding strength is measured by selecting a sample of sprayed fiberglass from a predetermined testing coupon, typically selected from the weakest part of, in this case, the shower stall. The objective of the R&D effort is to maximize bonding strength. Your team has settled on 6 variables and 1 interaction for this experiment. This totals 7 effects that we wish to study. Since this is a variable screening experiment, only 1 sample will be taken per trial. The team has decided to use the L8 array with 7 columns for factor assignment, and this will handle all 6 variables plus the interaction of interest. So the team has considered this list of factors that they figure are the most important with respect to fiberglass bonding strength. Dust in the air, cleaning procedure, resin supplier, resin mix, mold size, and cleaning solvent. And they've labeled them A through F. Level 1 is the current level, and level 2 is the level that they consider might be an improvement in each one of these factors. In addition, the team also wishes to study the CD interaction as they suspect that their suppliers make a different seasonal blend. C is resin supplier and D is resin mix. This is the Taguchi L8 orthogonal array. Across the top, factors 1 through 7, and across the side, trials 1 through 8. And in the middle, the ones indicate the current level, the 2 indicates the proposed level. So since a team is interested in an interaction, they start by finding a set of 3 columns in the orthogonal array that will jointly contain the 2 factors and their interaction. They'll examine that by use of a linear graph, which we see on the right-hand side. And then the team conducts the testing. So this slide contains a couple of things. It contains the assignment of factors that the team has determined, which factor should go into which column. So the team is mindful of the time and effort it takes to change, for example, factor C, which is resin supplier. Apparently that's very, very difficult, so they assign that to column 1, and it only has to be changed once between trial 4 and 5. And factor B, which is cleaning procedure, and that's been assigned to column 3. The team runs the experiment, and we have the results on the right-hand side. We run the experiment, and then we're going to create a supplementary table because that's going to be useful for us making calculations. For each factor in the experiment, we'll add all the results at level 1 and then record them in the table. We'll do the same for level 2. It is very useful to build a supplementary table. First off, it's a way for the team to look at each of the factors and consider the contrasts, the just numerical difference between level 1 and level 2. In our case, we've constructed the supplementary table by following the numbers. Let's go through factor A, that's in column 2. And we've added up all the ones, 84 plus 96 plus 94 plus 91, to give us 365. That number goes into the column 2 for factor A, 365. And then the complement of that, 89 plus 97 plus 94 plus 92 equals 372. That goes into column 2. Of course, each of the columns should add up to 737. You'll recall that we're going to be using analysis of variance as a technique to analyze our experiment. And we're going to be calculating a series of variances. Of course, the general formula, as you recall, is on the right. Well, Taguchi and his team recommend that we use a little bit of a shortcut that's called a correction factor. The correction factor will be used to help us analyze the numbers and create our F table. So the correction factor breaks the numerator of the variance, sometimes called the sum of squares, into 2 pieces. The correction factor, or what we'll call CF in the future, is the sum of the individual measurements squared divided by the number of measurements. So you recall the sum of all the measurements is shown in the supplementary table. The sum of each of the columns is 737. Therefore, our correction factor is 737 squared divided by 8, and that is 67,896. That's the correction factor. Well, now that we've calculated our correction factor, we can finish calculating the first of our sum of squares terms, and that's the ST, or the total sum of squares. ST is derived by adding up the squares of each of the results in our experiment and then subtracting the correction factor. So it's 84 squared plus 96 squared plus 89 squared all the way to 92 squared. And from that, you subtract 67,896, which is the correction factor. And if you do that bit of arithmetic, you'll see that the total sum of squares, ST, is 122. Main effect sum of squares is one of the things that we really want to concentrate on. These are the effects that we expect to come out with in the experiment, where we're trying to contrast the impact of each of the factors, A1 versus A2, B1, B2, and so forth. And we want to find out which one of these that the team thought really made a difference, indeed do make a difference, and by how much. So the general calculation for the factors is shown on the right. However, for a two-level experiment, an easier method for calculating the sum of the squares for the factors is shown below, where the sum of squares A is A1 minus A2 squared divided by n. Again, in this case, the variable n represents the total number of observation in the experiment. Back to our supplementary table. So for our current problem, let's just take sum of squares A, 365, refer to the supplementary table under column 2, 365 minus 372 squared divided by 8 equals 6. 8 is the n number of trials that we performed. If you go through the same calculation with the other main effects, you'll find that the sum of squares B is 3, sum of square C is 3, and so forth. Let's talk a bit about interaction. The interaction effect depends on looking at all the combinations of C and D at their different levels. A table can be made as follows. So across the top, factor C, across the side, factor D, and an interaction table is C1D1, C2D1, C1D2, and C2D2. Those are the possible interactions between C and D. In a two-level orthogonal array, the interaction can also be calculated just as we have calculated the main effects, using the levels, either 1 or 2 of the column that contain the interaction. In this case, if you look back in column 5. So our calculation for interaction would be those items found in the C and D column, that would be column 5, 84 plus 89 plus 91 plus 92 minus the 96, 97, 94, 94, or the difference between 356 and 381 squared divided by 8 is 78. So that's our sum of squares for our interaction. So next step is that we're going to calculate variances out of the sum of squares calculations. So far, we've calculated the sum of squares for the different factors. That's the top part, the numerator of the formula for variance. To form variances out of these sums, we have to divide them by the degrees of freedom. The degree of freedom, if you recall, is one less than the number of terms used to calculate the sum of squares. So designed experiments are analyzed using analysis of variance that we've discussed. And I just want to chat about some of the terms I've been using. Let's talk about the table that we're going to construct. In the column called source, those are the factors that we've been talking about, A, B, C, D, E, and F, and the interaction between C and D. The degrees of freedom, or the DF column, those are going to be 7, which is one less than the number of items required in our calculation. The sum of squares, that's the calculation that we've just performed for both the individual factors and the interaction. The variance, of course, is the sum of squares divided by the degrees of freedom. So let's just say in the first row, sum of squares is 6 divided by 1, so the variance is 6. In the CD interaction, the sum of squares is 78 divided by 1, so the variance is 78. And the F value is the ratio between the variances. And If you recall, we chatted about that in the previous presentation. Now, the F ratio is key to our understanding and analysis of the analysis of variance. So here is our table that we have. We showed this in the previous slide. And the next step is that we're going to calculate the F ratio from our variances and degrees of freedom. Using the ANOVA technique, remember that we're going to be using this as a test of hypothesis, and is based on estimates of the variance selected from the normal distribution. So if you recall early on when we talked about the design experiments, we assumed that the data is going to be drawn from distributions that are normal. The different estimates of the variances then are going to be used to form ratios, which is the F distribution is a distribution of variance ratios. In the case of designed experiments of any kind, we are going to be talking about between variation and within variation. Between variation is represented by any changes in the data brought about by changing the levels of the factor. So if you see just to the right, column 1, we went from we had 8 trials, and between trial 4 and 5 is when we switched from the lower level to the higher level. That's represented by considered between variation. Within variation is represented by the variation in the data that's not associated with the change of the factors. This can be considered experimental error. So between variation, in this case, is when we change factors from one level to another, and within variation is the variation within the trial. In most classical experiments, error variances are arrived at by selecting more than one sample for each setup. That's called repetition. We didn't do that in our fiberglass tub experiment. Or we can do it by replicating the setups more than one time. And since this was a sort of a screening experiment, we didn't do that either. In a Taguchi design, we can determine estimate error from a blank column. Now, we didn't do that in this particular example because we filled up all the columns, but in the next example, you'll see how we pull that error estimate out of a blank column. So like the SPC control chart, the F-test works by comparing within variation to between variation. So again, the F rate is a ratio of variances between and within. The F value therefore consists of the ratio of between variation contained in the data set to the within variation in the data set. So you remember in our particular experiment, we filled up all of the 7 columns with either factors or an interaction. So we didn't leave an empty column for us to determine our experimental error. So by pooling the error, we can determine our experimental error by bringing together those factors that are not significant compared to others. In this context, pooling means to add up all of the sum of squares for the insignificant factors and divide the total sum of squares that we found by the combined degrees of freedom for those factors. You'll see what I mean in a second. There are 2 rules of thumb regarding pooling. First, factors that have an F value of less than 2 are candidates for pooling. If an F value is less than 1, it should definitely be pooled. Second, if all the columns are used and there is no error term to use, pool until about half the degrees of freedom are included in the error. 2 sort of rules of thumb. In our experiment, the effect of D, which is found if you go down the source column and read across, and the interaction CD are very large compared to other terms. You can see that the sum of squares of D is 28, and the sum of squares of the interaction is 78, and therefore the variances are 28 and 78 respectively. While the rules say that we should pool until 3 or 4 degrees are included in the error term, in this case, it makes sense to include 5 similar factors in the error term. So we've pooled all the other sources of variation because they're so much smaller than the main effects D and the interaction CD. So we're going to pool source A with a variance of 6, source B with a variance of 3, source C with a variance of 3, source E with a variance of 1, and source F with a variance of 3 into a pooled variance, adding up all of their sum of squares and their degrees of freedom. And we're going to use them as in our factor for calculating the ratio of variances between D and the pool variance and CD and the pool variance. So if you divide 28 by 3.2, you'll find that that's F ratio of 8.75. And if you divide 78 by 3.2, you'll find that that ratio is 24.38. So now that we've pooled and calculated our ratio of variances of the factors that are indeed significant, factor D and the interaction of C and D, we now have our completed ANOVA table. So at this point, we want to determine if the apparently significant factors are indeed statistically significant. And we do that by consulting the F tables. So the two F values in the ANOVA table are now compared to an F table. Remember from our earlier discussion, we'll need a few items. We'll need the alpha value, the value of the risk that we're going to take, the degrees of freedom in the numerator, the degrees of freedom in the denominator to use these tables. So we're going to check the significance of our two factors at the 5% level. We find a chart that says critical values of the F distribution, alpha equals 0.05. The critical number for degrees of freedom of 1, find the column, degrees of freedom 1, and then read down to see the row, degrees of freedom 5, is 6.608. And if we wanted to take this a bit beyond that and determine what it would be for a 1% error rate, I've shown the 1% table and the same item here with degrees of freedom 1 and degrees of freedom 5. The critical value for 1% error is 16.26. So oftentimes we want to provide a visual explanation of the main effects and of the interactions. So it's not that unusual to make these graphs as a part of any presentation on a designed experiment. These graphs are developed using the supplementary table and using the totals for the factors at each level. The average value is found by dividing the total by the number of terms included in it. For this experiment, we're going to divide each total by 4 because there were 4 trials within each factor. And to the right, we have our supplementary table that we built a few slides ago. So if you perform that for main effect A, you can see the effect of factor A. At level 1, the average effect is 91, and at level 2, it's about 93, not very much of a difference. And you can do that for each one of the main effects. Building the interaction, and since the interaction in this particular experiment was highly significant, we'll want to perform that, and you'll go into the table and select the cells, and you'll be dividing those by 2 because we're going to be going into each of the individual pairs of cells. Graphing interactions is very interesting. So you see our 2 lines, D at level 1 and D at level 2, cast against factor C at level 1 and C at level 2. So it's likely that only factor D produces a significant effect on the process. All other variables, at least within the ranges of the levels tested, have negligible effect on adhesion. However, we know that factor C interacts with factor D to produce an even more significant effect on the process. While factor C is not by itself significant, but the way it interacts with D is very, very important. So where do we go from here? Well, if we were running the experiment to improve a process, we would verify the results by performing a confirming run. And assuming that the results are reproducible, we would then set the two significant factors at their optimum level. And if nothing else is impacted, we'd consider the potential for cost reduction by setting the other non-significant factors at the cheapest, most easiest operational level. However, if we were doing this experiment as a screening run, that is to determine which variables were indeed most important, we would isolate factor D and the interaction for a more detailed study and eliminate the others. So again, setting up the experiment is the most important thing. Working with the team is extremely important. And oftentimes people get fumbled around with the calculations. These days, software makes the calculations easy. Here's one software that I've used for a number of years for a number of applications. You might consider this or others. I'd like to thank you for your attention here in this part of our practical problem solving clinic, experimental techniques. Please proceed to part 5, where we'll operate a different designed experiment for using Taguchi techniques. Again, thank you to the Greater Detroit section for the American Society of Air Quality for introducing me to hypothesis testing and so many other items in terms of quality and productivity improvement, and to the Ford Motor Company and their work with the American Supplier Institute, Genichi Taguchi, and Yuan Wu, who wrote Offline Quality Control. And again, my colleague, Mr. Tom Dole, for his enduring work in training and continuous improvement. Thank you very much.